Welcome to the Deep Dive. Today, we're tackling ice ages, a topic that probably brings up images of, mammoths and vast frozen plains. And while that's definitely part of the story, here's something interesting. Geologically speaking, we're actually in ice age right now.
That's right. It surprises a lot of people.
So what we usually think of as the ice age, those really intense glacial periods, they're more like phases within this much longer thing called an ice epoch.
Exactly. And our current warmer period, it's just a relatively short break in interglacial.
Okay, so let's get into why understanding this whole long-term icy situation matters, especially now.
Well, it's fascinating if you step back and look at Earth's history. For most of it, the planet's been much, much warmer than it is today.
Really? Significantly warmer?
Oh, yes. Having polar ice caps, especially two at the same time like we do now, is actually quite rare geologically. And in fact, this relatively unusual icy state we're in might even be connected to, well, how we evolved, our own evolution.
Wow, hold on. Ice caps possibly playing a role in making us human. That's a mind blower.
It's a compelling idea we can explore.
Okay. Now, when we talk climate, we often focus on the day-to-day weather, right? Temperature, rain, pressure, that kind of stuff.
The short-term fluctuations.
But the real climate drivers, the big forces with long-term impact, are things like ocean currents.
Absolutely. Think of them like enormous rivers, but carrying heat instead of just water, moving warmth from the equator up towards the poles.
And their power is just immense, isn't it?
To really get a sense of it, look at northwestern Europe. It's way milder than, say, parts of Canada at the exact same latitude.
Right, like comparing Ireland and Labrador or something.
Exactly. The Gulf Stream, sort of steered by North America's geography, acts like a giant natural radiator for Europe. It releases heat, making places like the UK much warmer than they'd otherwise be.
Anyone who's been through a proper Canadian winter at that latitude knows it's a completely different world, an ice age world almost.
We're definitely in a different climate regime.
And this whole system, this heat transport, it's quite delicate, which leads to a really counterintuitive possibility, even though we're seeing overall global warming, which most scientists attribute to, human activity. We could actually see northwestern Europe get colder.
It sounds completely backwards, doesn't it? But there's a mechanism.
How does that work?
Okay, so the Gulf Stream is just one part of this huge global system, often called the ocean conveyor belt. Warm, salty water flows north near the surface.
Carrying incredible amounts of heat.
Staggering amounts. Then, when it gets way up north in the Atlantic, it cools down, releases that heat, and crucially, it gets saltier because of evaporation.
Okay.
And this cold, salty water is denser, so it sinks. This sinking action acts like a giant pump, driving the whole conveyor belt. We're talking a flow vastly greater than all the world's rivers combined.
Right. So the warming connection. Melting ice.
Precisely. If you pour huge amounts of fresh water from melting Arctic ice into that North Atlantic pump, well, it's like adding fresh water to salt water. It dilutes the salinity.
Making it less salty, so less dense.
And if it's not dense enough, it might not sink as effectively. The pump could weaken or potentially even shut down.
And if the pump stops,
then that warm Gulf Stream water might not get pulled as far north. Northwestern Europe could lose its radiator,
leading to significant cooling there, even as other parts of the world warm up.
Some models even suggest a really dramatic flip. Europe getting a climate more like coastal Canada, while Canada might actually get milder, maybe more like Ireland.
That sounds extreme.
It does, but the heat carried by the Gulf Stream is immense. Someone calculated it's like a million one-bar electric fires constantly running. So messing with it would have huge consequences.
It really underscores how interconnected and sensitive the climate system is. And that brings us to the main focus of our deep dive today. We're not just looking ahead. We want to go way back to the Victorian era and explore the really fascinating story of how scientists even figured out the concept of ice ages.
It wasn't obvious at first. It started with some very strange clues in the landscape.
Clues like?
Like erratic boulders. These massive rocks, sometimes the size of houses, found sitting in places miles and miles away from any bedrock they could possibly have come from.
How did they explain those initially, back in the 17th, 18th centuries?
Well, the dominant idea was the biblical flood. These huge rocks, piles of gravel and sand scattered across hills, it all seemed to fit with a massive, catastrophic flood sweeping across the land.
Part of that whole catastrophism view, right? Earth shaped by sudden big disaster.
Exactly. The flood was seen as the most recent big one, a divine intervention.
But then thinking started to shift, didn't it? Towards the end of the 18th century.
Yes, toward uniformitarianism. Thinkers like James Hutton were key here.
The idea that the slow, everyday geological processes we see, erosion, sedimentation, volcanic activity, could shape the entire planet if given enough time.
Immense stretches of time, yes. It was a revolutionary idea. In this view, something like an ice age wasn't a one-off divine cataclysm, but part of the Earth's long natural cycles. Still dramatic for anything living through it, of course.
But the specific idea of an ice age, it was still kind of on the fringes for a while.
It was, until the 1830s. That's when a Swiss scientist, Louis Agassiz, really grabbed hold of it in 1837 and pushed it forward.
Agassiz, what was his background?
Interesting, actually. Trained in medicine, but his real passion was natural history, fossils, that sort of thing. And crucially, he was influenced by Georges Cuvier, who was a major proponent of catastrophism.
So he came from the catastrophist school of thought initially.
He did, which makes his eventual championing of the Ice Age theory even more interesting.
And things were also happening independently in Switzerland, right? Before Agassiz jumped in.
Yes, absolutely. There was a local observer, a chamois hunter actually, named Jean-Pierre Perraudin in the Val de Bagne. He noticed these strange scratches, grooves on the rocks high up the valley sides, and these erratic boulders.
And he thought,
he became convinced the local glacier must have once been far, far bigger, filling the whole valley and leaving those marks as it moved. Around 1815, he told a geologist, Jean de Charpentier, about it.
how did de Charpentier react?
Well, de Charpentier managed the salt mines nearby, was interested in geology, and was already doubting that water alone could move those huge erratics. But Perraudin's idea of a giant glacier, he thought it was a bit too much, initially dismissed it.
But Perraudin didn't give up.
Nope. He found someone more receptive, an engineer named Ignace Venetz. Venetz had seen similar things, piles of rock debris, what we now call moraines, way down valley from existing glaciers.
Ah, the telltale signs of glacial deposit.
Exactly. By 1829, Venetz proposed something even more radical, that glaciers hadn't just flowed down valleys, but had once formed a massive ice sheet covering Switzerland, the Jura Mountains, maybe even wider.
And this time, de Charpentier listened.
This time, he was convinced. The evidence Venetz had gathered was compelling. De Charpentier encouraged Venetz to publish, did his own fieldwork, and prepared his own paper.
And Agassiz heard about this.
He was in the audience when de Charpentier presented his findings in 1834, and Agassiz's reaction: deep skepticism. Just like de Charpentier's initial reaction to Perraudin.
History repeating itself.
Sort of. Agassiz actually went on a field trip to the area near Bex in 1836, specifically intending to disprove de Charpentier's glacial theory. He still favored the idea of giant icebergs floating in a massive flood carrying the boulders.
But the evidence changed his mind.
Completely. Seeing the polished, striated rocks, the huge moraines firsthand, it was a total conversion. He didn't just accept the Ice Age idea, he became its most fervent champion. And he envisioned it on an even grander scale.
Grander how?
He imagined a colossal ice sheet stretching from the North Pole all the way down to the Mediterranean, burying Europe, a truly vast glaciation.
Wow, so when he announced this,
it was pretty dramatic. At a meeting of the Swiss Society of Natural Sciences, he talked about a complete break between the present creation and those which preceded it. Very catastrophist language. Remember, this is pre-Darwin.
how did that go down?
Mixed reactions, to say the least. A lot of disbelief, even ridicule. He organized a field trip to the Jura Mountains to show the evidence. Some opponents apparently claimed the clear glacial scratches on the rocks were just damage from carriage wheels.
You're kidding? Carriage wheel.
That's the story. Shows the resistance he faced.
But Agassiz wasn't put off.
Not at all. For him, this ice age wasn't just geology. It had huge implications for understanding life. He argued it explained gaps in the fossil record.
Oh, so?
He thought if species looked similar before and after the Ice Age, it wasn't direct descent. It was God repopulating the Earth with similar but new creations after the cataclysm wiped things out. Remember, this is 1837. Origin of species was still over 20 years away.
So it fit a kind of catastrophist pre-evolutionary view.
Yes,
Yeah.
which is why the uniformitarians, like Charles Lyell, were initially very resistant. Agassiz was apparently quite disappointed when even William Buckland, a known catastrophist, didn't immediately buy into it during a visit in 1838.
So Agassiz doubled down on collecting evidence.
Absolutely. He did really careful work, like measuring glacier movement on the Our Glacier. He put stakes in the ice and tracked their downhill progress year after year.
Direct proof of ice flow.
Mm-hmm. He noted a cabin built by a previous researcher, Hugi, had moved something like 4,000 feet down the glacier since 1827. Concrete evidence of the power involved.
And then he published his big book.
Yes, Études sur les glaciers, Studies on Glaciers in 1840. It was hugely influential. It painted this incredibly vivid, almost terrifying picture of vast ice sheets grinding across continents.
Can you give us a flavor of that?
He wrote about Europe being buried under ice, the silence of death hanging over the land, only the whistling winds and the cracking of ice breaking the stillness. Really powerful imagery.
Wow. And he took this idea to Britain.
Same year, 1840, presented it at the British Association meeting in Glasgow. Predictably, Lyell, the arch-uniformitarian, was still skeptical.
But Buckland was there too, the catastrophist who had been hesitant before.
He was, and this time his mind was more open. He invited Agassiz and another geologist, Murchison, on a field trip to Scotland.
And Scotland showed them the evidence.
It did. The Scottish Highlands have classic glacial features. Buckland was finally convinced, and Agassiz found even more proof for his theory.
Buckland's conversion must have been significant.
Hugely. He immediately went to see Lyell, who was also in Scotland, and showed him clear moraines, those glacial debris ridges near Lyell's own family home.
And Lyell.
Apparently, Lyell, who'd been puzzled by deposits like that for years, instantly saw the light and accepted the Ice Age theory. Buckland wrote excitedly to Agassiz saying Lyell had adopted it in toto, seeing it explain so many geological puzzles.
So the idea was finally gaining real ground.
Yes, Lyell even agreed to map and describe the glacial features for the Geological Society. The Ice Age, once dismissed, was becoming mainstream science.
Okay, so the geological evidence was building. The next big question must have been, what on earth could cause something like that? A massive recurring ice age.
Exactly. And the first real attempt at an astronomical explanation came just a couple of years later in 1842 from a French mathematician, Joseph Adamar.
Adamar. Was his idea right?
Not really. His specific model was flawed, but it was important because he based it on a key astronomical fact. Earth's orbit isn't a perfect circle.
Right, it's an ellipse.
Yeah.
Kepler figured that out centuries before.
Which means sometimes we're closer to the sun, that's perihelion, and sometimes farther away, aphelion. So the intensity of sunlight we get varies slightly through the year.
And we also have the Earth's tilt causing seasons.
Yes, the axial tilt, currently about 23.5 degrees. That's the main reason for seasons, not the distance the northern hemisphere has summer when we're actually farthest from the sun.
So what was Adamar focusing on?
He focused on something more subtle, the precession of the equinoxes. It's like the slow wobble of a spinning top. Earth's axis does this wobble over a cycle of about 26,000 years.
And that affects?
It affects when the seasons occur relative to our position in the elliptical orbit. So about 11,000 years ago, the northern hemisphere winter happened when Earth was at a different point in its orbit, and the winter was actually longer than the summer back then.
Okay, so how did Adamar connect this wobble to ice ages?
Well, this is where he went a bit wrong. He incorrectly thought the longer winters in one hemisphere would make it significantly colder overall. He pointed to Antarctica being frozen and blamed longer southern hemisphere winters.
And proposed alternating ice ages.
Yeah, he suggested ice ages would switch between north and south hemispheres roughly every 11,000 years, tied to this precession cycle.
Didn't he have an even wilder idea, too?
Oh, yes. He suggested the massive ice buildup in Antarctica would gravitationally pull the ocean south, causing northern ice ages, and then, when the Antarctica ice melted, catastrophic tidal waves. Very dramatic.
Still thinking in catastrophist terms, then.
A bit, yes, but credit where it's due. He was the first to really propose that these cyclical changes in Earth's orbit could be the pacemaker for recurring ice ages.
But his core mechanism was flawed.
Fundamentally, about 10 years later, the famous scientist Alexander von Humboldt pointed out the big problem.
Which was?
Over a whole year, each hemisphere actually gets the same total amount of heat from the sun, regardless of these orbital variations. A longer, milder winter is balanced by a shorter, hotter summer, and vice versa. So Adamar's main idea for one hemisphere getting colder just didn't work physically.
Okay, so Adamar's attempt didn't quite pan out. Who came next?
Enter James Croll, a really fascinating character. A self-taught Scottish scientist working in the second half of the 19th century.
Self-taught?
Completely. His formal schooling ended early. He worked all sorts of manual jobs: millwright, carpenter, tea merchant, hotel keeper, insurance salesman, you name it.
Wow. But he kept studying on his own?
Absolutely. He had this incredible intellectual drive, read voraciously, taught himself physics, astronomy,
Amazing persistence.
and then he landed a job that was, well, a bit of a breakthrough for him. He became a janitor at Andersonian College and Museum in Glasgow.
A janitor.
Yes, but crucially, it gave him access to their excellent scientific library. Imagine after all those years studying alone.
What an opportunity.
It really was. He soaked it all up. Even published a paper on electricity while working as a janitor. By the 1860s, ice ages were a hot topic again, partly tied into the debates around Darwin's relatively new theory of evolution. Croll got interested.
He came across Adamar's work.
He did, saw its flaws, but felt the basic idea astronomical cycles driving ice ages had to be right somehow.
And Croll had access to something Adamar didn't fully grasp, right? Another orbital variation.
Yes, a crucial piece. The shape of Earth's orbit itself changes, its eccentricity. It cycles between being more nearly circular and slightly more elliptical.
And that cycle length is?
Roughly 100,000 years. This variation in eccentricity had been calculated by the French astronomer Urbain Le Verrier.
Le Verrier. Guy who predicted Neptune.
The very same. His calculations showed how Earth's eccentricity had changed over the past 200,000 years.
And Croll thought this might be the key.
He speculated that periods of high eccentricity when the orbit is more stretched out might be linked to ice ages. He published some initial thoughts in 1864.
Which got noticed.
It did. Generated enough interest that he was encouraged to pursue it further. He ended up writing a major book in 1875, Climate and Time. He even got a job with the Geological Survey of Scotland and became a Fellow of the Royal Society. Quite a journey from being a janitor.
So how did Croll refine the astronomical theory? He used Le Verrier's formulas.
Yes, he used them to calculate eccentricity much further back in time, plotting it out, finding these long intervals of high eccentricity separated by even longer periods of low eccentricity.
And his key idea was about the distribution of heat.
Exactly. Not the total heat per year, but how it was spread between seasons. He thought that during periods of high eccentricity, if precession meant winter occurred when Earth was farthest from the sun, those winters would be exceptionally cold.
Leading to more snow.
More snow sticking around, yes. And crucially, Croll recognized the importance of feedback. More snow and ice reflects more sunlight back to space, the albedo effect. This makes things even colder, allowing ice sheets to build up.
So he was early in thinking about climate feedbacks.
He really was, even though the specific detail about which season mattered most turned out to be wrong. We now know it's cool summers, not cold winters, that are critical for building ice sheets.
But he saw the feedback loop. What was his overall prediction?
He still thought ice ages should alternate hemispheres every 11,000 years or so due to precession. But he linked the major ice age periods to those long stretches of high orbital eccentricity, suggesting the last big peak was maybe 100,000 years ago, followed by a long interglacial.
Did he consider other factors like ocean currents?
He did. He linked ocean currents to trade winds and suggested, much like we discussed earlier, that small changes in Atlantic currents could drastically change Europe's climate. He understood there was this global river of currents.
And the third orbital factor, axial tilt.
He knew about that too. Variations in Earth's tilt calculated by Le Verrier, based on earlier work by Laplace. Croll thought less tilt might favor ice ages by reducing summer heat at the poles.
So by 1875, Croll had identified all three main astronomical factors: eccentricity, precession, and tilt.
That's right. All the ingredients were on the table, even if the recipe wasn't quite right yet.
How was Croll's theory received initially?
Quite positively. The geological evidence for multiple repeating ice ages was growing, so a cyclical astronomical cause seemed plausible.
But there were problems later on.
Yes, the big one was dating. They didn't have precise ways to date past ice ages back then. By the early 20th century, geological evidence started showing the last ice age ended much more recently than Croll predicted, maybe 10,000 years ago, not 80,000.
A big discrepancy.
Huge. And some climate changes seemed to happen at times when Croll's model predicted the opposite. So his specific model started to fall out of favor. The core idea of astronomical influence remained, but Croll's mechanism seemed flawed.
So the stage was set for someone to put the pieces together correctly.
Exactly. And that person was a Serbian engineer named Milankovitch.
Milankovitch.
Yeah.
Born when?
1879. He picked up the astronomical theory and decided to tackle the immense task of calculating the combined effect of all three cycles, eccentricity, tilt, and precession on sunlight, reaching different parts of the Earth at different times.
And this was against a backdrop of, well, significant political turmoil in the Balkans.
A very volatile time and place, yes. Interestingly, his first interest wasn't even Earth's climate.
Oh, what was it then?
He wanted to apply his maths to other planets, especially Mars. This was the era of fascination with Percival Lowell's canals on Mars and speculation about extraterrestrial life.
But he turned his attention to Earth's ice ages. And the calculations must have been staggering.
Unbelievably complex, and he did it all by hand. No computers. His big advantage was that a German mathematician, Ludwig Pilgrim, had published detailed calculations of Earth's orbital parameters going back 1,000,000 years in 1904.
So Milankovitch had the raw orbital data.
Yeah.
His job was to figure out the sunlight effect.
Precisely. How much solar energy or insolation hit any given latitude during any given season, accounting for all three constantly changing orbital factors. A monumental undertaking.
He had a very specific routine for this work, didn't he?
Extremely disciplined. Early starts, intense work, specific coffee and pipe breaks with the window open, precise lunch, siesta, more calculations than an evening walk, dinner, and reading totally unrelated stuff to rest his brain.
Wow. Did he hit roadblocks?
He did. Significant mathematical hurdles initially. The breakthrough apparently came during the First Balkan War in 1912. He was serving in the army and amidst the chaos had a flash of insight that solved a key problem.
Strange place for a scientific breakthrough.
Isn't it? He published some early results in Serbian, but they didn't get much international attention.
And then World War I happened.
Yes, and ironically, it gave him the time he needed. He was captured by the Austro-Hungarian army.
Oh, dear.
But remarkably, they let him continue his work while imprisoned. He later said his cell felt like night quarters on my trip through the universe. Incredible focus.
How long was he imprisoned?
Not too long. An academic colleague intervened. He was paroled to Budapest, had to report to the police, but crucially got access to the library of the Hungarian Academy of Sciences.
So he had uninterrupted research time.
4 years of it. This led to his big book, published in French in 1920. Still, it didn't immediately grab most geologists' attention.
But someone important noticed.
Yes, Vladimir Koppen, a hugely respected German meteorologist, famous for the Koppen climate classification system we still use variations of today.
Koppen.
Koppen saw the significance of Milankovitch's incredibly detailed calculations, and Koppen was working closely with his son-in-law, Alfred Wegener.
Wegener, of continental drift fame.
The very same. Koppen and Wegener discussed and promoted the Milankovitch model in their own influential book in 1924.
And Koppen added a crucial piece to the puzzle, didn't he? Something that changed how the model worked.
He did. This was perhaps the key insight. Adamar and Croll had focused on cold winters building ice. Koppen realized that's not the main driver in high latitudes.
Why not?
Because it's always cold enough for snow in winter there. The critical factor, Koppen argued, is the summer. If summers are too cool to melt the previous winter's snow.
The snow builds up year after year.
Exactly. It accumulates, compacts into ice, and the growing white surface reflects more sunlight. That albedo feedback Croll also recognized, making things even colder, allowing glaciers and ice sheets to grow.
So it's about cool summers, not cold winters.
Yeah.
That completely flips Kroll's idea.
It does. Suddenly, the astronomical model predicted intense cold around 80,000 years ago, when summer sun was weak in the north, not warmth. And it predicted warming around 10,000 years ago, leading into our current interglacial, matching the geological evidence much better.
Milankovitch must have taken that on board.
He did. He then redid huge parts of his calculations, focusing specifically on summer heating at key northern hemisphere latitudes like 65 degrees north over the past 650,000 years.
And the results?
His new curves showed these clear dips or notches representing cool summers. Koppen could match these notches pretty well with the known advances of glaciers in the Alps. These curves in the Koppen-Wegener book were what really brought the theory to wider notice.
So Milankovitch kept refining this, identifying the specific rhythms.
Yes, over the next decade or so, he nailed down the influence of the roughly 100,000-year eccentricity cycle, the 41,000-year tilt cycle, most important at high latitudes, and the roughly 22,000-year precession cycle, more influential, closer to the equator.
And combined them into a full model.
A comprehensive mathematical model showing how these cycles interacting would drive ice sheets forward and back. He even tried to link it empirically to the observed snowline altitude in different regions.
When did he publish the definitive work?
His magnum opus, Canon of Insulation and the Ice Age Problem, came out in 1938, right before World War II, a lifetime's work. He remained quietly confident in it, even when its popularity dipped in the 50s.
And there's a modern understanding of this that's quite profound, isn't there? About the natural state.
Yes. The realization that, given Earth's current geography, the default climate state is actually a deep freeze, a full ice age.
And the warm periods, the interglacials, like ours, are the exception.
Exactly. They only seem to happen when all three Milankovitch cycles line up just right to give the northern hemisphere unusually warm summers, enough to melt back the ice. Otherwise, Earth tends towards glaciation.
That explains the pattern of long cold spells and short warm spells over the last few million years.
It does. Back in the 20s and 30s, they thought ice ages only happened during the biggest dips in Milankovitch's curves, with long, warm periods between. The geological records seemed to fit that roughly, which gained the model some support, especially in Europe.
But there were still issues, besides the summer-winter confusion.
The big lingering problem was dating. They still lacked truly independent, precise ways to date the geological evidence of past ice ages. Sometimes they even used Milankovitch's curves to date the deposits.
Which is circular reasoning, really.
It is. You can't use the theory to date the evidence you're using to test the theory. They needed independent dating.
And that arrived after World War II.
Yes, the big game changer was radiocarbon dating, developed in the 1950s, measuring the decay of carbon-14 in organic remains.
That must have helped pin down recent events.
Immensely. It gave much better dates for the end of the last ice age, confirming a late peak around 18,000 years ago, and a rapid melt starting around 10,000 years ago. It revealed a more complex recent history.
But radiocarbon dating has limits, doesn't it? Doesn't go back far enough for the really long cycles.
Exactly. It's only good for about 40,000, maybe 50,000 years, max. So it couldn't directly test the big 100,000-year Milankovitch cycle, or even the 41,000-year one reliably.
So attempts to use it to test the model were
A bit shaky. Some early studies using the limited radiocarbon data seemed to contradict Milankovitch's insolation curves for certain periods. This actually led to the model falling out of favor again in the 1960s.
So the astronomical theory was on the ropes again.
It seemed that way. But looking back, the evidence against it was pretty thin, based on incomplete data. What they really needed was a way to get a continuous global climate record stretching back hundreds of thousands of years.
Sort of natural climate archive.
A natural global geological thermometer, you could call it.
And the answer lay on the ocean floor.
Yes, deep sea sediments. Even Croll had hinted at this potential way back. The idea is simple. Tiny marine creatures live in the surface waters. Different types prefer different temperatures. When they die, their shells rain down onto the seabed,
Building up layers over time.
millennia after millennia, creating a layered archive of past ocean conditions and therefore past climates.
When did they first realize this?
The HMS Challenger expedition in the 1870s dredged up deep-sea mud, or ooze, and found it was full of these microscopic shells, foraminifera, radiolaria. Hints of the climate story were there.
But getting long, undisturbed samples was the challenge.
Exactly. That needed technology. The breakthrough was the Kuhlenberg piston core, developed mid-20th century. It could punch down and pull up long cylinders of sediment, sometimes tens of meters long.
Opening up millions of years of history.
Potentially, yes. Sedimentation rates very slow in the deep Pacific, faster in the Atlantic, giving more detail over shorter timescales there. Early core studies quickly showed evidence for many repeated ice age cycles.
Were specific institutions leading this?
Lamont Doherty Geological Observatory, associated with Columbia University, became a major player from the 1950s onwards, building a huge library of these deep-sea cores.
And researchers started analyzing the shells.
People like David Erickson and Guesta Woolen at Lamont did meticulous work, identifying the types of plankton shells in different layers of Atlantic cores.
What did they find?
They confirmed the big warming around 11,000 years ago, but also tracked climate changes much further back. They identified shifts in plankton populations that suggested the start of the main Pleistocene Ice Age phase was around 1.5 million years ago.
Okay, so analyzing the types of creatures. Was there another technique coming online too?
Yes, a really powerful one, oxygen isotope analysis, developed at the University of Chicago.
Oxygen isotopes, how does that work?
It looks at the ratio of two types of oxygen, the common oxygen-16 and the rarer, heavier oxygen-18 trapped in the calcium carbonate shells of those foraminifera.
And that tells you about temperature.
That was the initial idea. The proportion of oxygen-18 the creature incorporates into its shell depends on the water temperature when it was alive. Colder water means slightly more oxygen-18 in the shell.
Who pioneered applying this to the cores?
Cesare Emiliani. He analyzed cores and identified 7 distinct ice age interglacial cycles over the past 300,000 years. And he noticed the timing looked remarkably similar to the Milankovitch astronomical cycles.
So compelling evidence from Milankovitch.
It seemed like it. But Emiliani's interpretation that the isotope ratio was purely a temperature signal was controversial. Ericsson, for instance, disagreed, thinking other factors like salinity might be involved. And geologists were still generally skeptical of Milankovitch because of those earlier radiocarbon issues.
So more debate. How was it resolved?
A conference in 1965 tried to sort it out. A key figure there was John Embry, who developed sophisticated statistical methods to analyze entire populations of different form species together.
Trying to separate temperature from other effects.
Exactly. By looking at multiple species, he hoped to disentangle the influence of temperature, salinity, and other factors. His work, along with parallel isotope studies by Wallace Brucker and Jan van Donk, eventually confirmed the basic temperature signal in the isotopes.
Did they find Ericsson's doubts were valid?
Partly. Ericsson had relied heavily on one species, Globiritalium menardii, which turned out to be quite sensitive to salinity changes too, confusing the picture. But the overall temperature signal was real, though maybe smaller than Emiliani first thought, perhaps a 2 degrees C drop in tropical surface waters during ice ages, not 6 degrees C.
But then came an even bigger realization about the isotopes, right? It wasn't just temperature.
This was the absolute game changer from Embry and Nicholas Shackleton. They realized the oxygen isotope ratio in the shells wasn't just reflecting water temperature, it was also reflecting the total amount of ice on the planet.
How?
Because water molecules with the lighter oxygen-16 evaporate more easily from the ocean surface. This water vapor gets transported, falls as snow over land, and gets locked up in the growing ice sheets during an ice age.
Leaving the oceans behind, relatively richer in the heavier oxygen-18?
Precisely. So when foraminifera build their shells during an ice age, they incorporate more oxygen-18, not just because the water might be slightly colder, but mainly because the ocean itself has a higher O18-O16 ratio due to all that O16 being trapped in ice sheets.
Wow. So the isotope record in deep-sea shells is actually a proxy for global ice volume.
Primarily, yes. It became this incredible, continuous record of how much ice there was on Earth, a direct measure of the pulse of the ice ages, a truly global signal.
Okay, that's huge. Were other dating methods also improving?
Yes, techniques like uranium-thorium dating were being applied to things like ancient coral reefs, which record past sea level.
And sea level is directly linked to ice volume, right?
Absolutely. When ice sheets grow, sea level falls. When they melt, it rises. These dating methods started showing high sea levels, indicating warm, low ice periods around 125,000, 105,000, and 82,000 years ago, dates which lined up beautifully with predicted Milankovitch warm peaks. Wally Brucker did important work here with thorium dating.
And evidence from land, too.
George Kukla, working in Czechoslovakia, studied thick deposits of low S that's wind-blown dust from glacial times. He found evidence for 10 distinct cycles, dominated by a 100,000-year rhythm.
How did he date those?
Using another new tool, paleomagnetism, the discovery that Earth's magnetic field flips polarity periodically. These reversals get recorded in rocks and sediments as they form.
Like a magnetic barcode in the strata.
Kind of, yeah. By dating these magnetic reversals using other methods like potassium-argon dating on volcanic layers, scientists could build up a timeline. Researchers at Le Mans, like Bill Berggren and Jim Hayes, use this magnetic stratigraphy in deep-sea cores to establish firm dates for climate events, refining the start of the Pleistocene to about 1.8 million years ago.
So all these different lines of evidence were starting to converge.
Exactly, which led Jim Hayes to spearhead a major international project called climatic mapping starting in 1971. The goal was to pool all this data and expertise cores, isotopes, plankton analysis, dating to reconstruct past climates globally.
Was there a particular core that was especially important?
Yes, core V28238 from the Pacific. Nick Shackleton's incredibly detailed oxygen isotope analysis on this core became a benchmark, the Rosetta Stone for global ice volume changes over hundreds of thousands of years.
And could they see the Milankovitch cycles in that record?
They could analyze the data using statistical techniques like power spectrum analysis, looking for repeating patterns. The 100,000-year cycle came out strongly. The shorter cycles, the 41,000-year tilt and the 20,000-year precession, were hinted at, but not statistically crystal clear in that specific core, probably because the sediment accumulated quite slowly there.
So they needed a core with faster sedimentation, more detail.
Right. They found one in the Indian Ocean. Analyzing that longer, higher resolution core nailed it. Clear, statistically significant peaks in the climate variability at 41,000 years, and also at 23,000 and 19,000 years.
Wait, 23,000 and 19,000. Not just one 20,000-year cycle.
Correct. It turns out the precession cycle is actually split into two main frequencies due to subtle gravitational tugs from other planets. A Belgian astronomer, André Berger, confirmed this theoretically. The deep-sea record showed exactly those predicted frequencies.
That's incredible confirmation. The smoking gun.
Pretty much definitive proof. It all came together in a landmark paper in Science in 1976. Authors were Hayes, Embry, and Shackleton.
And the title?
Variations in the Earth's Orbit. Pacemaker of the Ice Ages. Couldn't be clearer. They concluded that orbital changes are the fundamental cause of the major ice age cycles of the last few million years.
Do they make any predictions?
Based on the ongoing orbital cycles, they predicted a long-term trend towards renewed northern hemisphere glaciation over the next several thousand years.
Wow. Was this widely accepted then?
It became the consensus view. Interestingly, that same year, 1976, a previously skeptical figure came out strongly in support.
Who was that?
Sir John Mason, head of the UK Meteorological Office, he did his own calculations, looking at the sheer amount of energy needed to melt the ice sheets at the end of the last ice age.
The latent heat of fusion.
Exactly. He compared the energy required to melt the ice with the extra solar energy received due to the Milankovitch cycles during the warming period. The numbers matched incredibly well. The energy surplus from the orbital changes was almost exactly what was needed to melt the known ice volume. The correlation held over something like 24 orders of magnitude. It was powerful physical confirmation.
So the case was pretty much closed. Milankovitch was right.
The fundamental mechanism was confirmed. The orbital cycles act as the pacemaker, triggering the shifts between glacial and interglacial states.
And our current warm period, the Holocene.
Peaked in warmth around 6,000 years ago, likely when all three cycles aligned for maximum northern hemisphere summer sun. Since then, the orbital factors have been shifting slowly towards conditions that favor cooling long-term.
One more thing on the cycles, do they happen at the same time in both hemispheres?
Surprisingly, yes. The major shifts between ice ages and interglacials seem to be globally synchronous. The pacemaker is the northern hemisphere summer insolation, but feedbacks involving ocean currents, greenhouse gases like CO2 seem to transmit the signal globally quite quickly.
So even though Antarctica stays icy, the whole planet feels the shift.
Broadly speaking, yes. Warm northern summers coincide with warmer southern winters, reducing sea ice around Antarctica, for example. The whole system shifts together.
Okay, let's zoom out one last time. Put this current ice epoch in the grand scheme of Earth history. It's relatively recent, isn't it?
Oh, very recent. Just the last few million years out of 4.5 billion. Geologists divide time into eons, eras, periods, epochs. Miocene, Pliocene, Pleistocene, Holocene are recent epochs.
And the Holocene, our current bit, is tiny. Just 10,000 years or so.
Almost comically short on a geological scale. Some argue calling it a separate epoch is a bit anthropocentric, really just the latest warm blip within the Pleistocene ice epoch.
Before this current ice epoch started a few million years ago, Earth was much warmer for a long time.
For tens of millions of years after the dinosaurs died out, yes, largely ice-free. Things started to change mid-Miocene, maybe 13 million years ago.
What happened then?
Antarctica finally drifted right over the South Pole. That allowed a permanent ice sheet to start growing there.
And other continental shifts played a role?
Yes, later, around 6 million years ago, South America and Australia pulled away from Antarctica, opening up the Drake Passage and allowing the Antarctic circumpolar current to form. This powerful current isolates Antarctica in cold water, locking it into a frozen state.
What about the northern hemisphere? Why did it start getting ice ages later?
Continental drift there gradually restricted the flow of warm water from the equator into the Arctic Ocean. This made the high northern latitudes much more sensitive to those Milankovitch variations in summer sunshine.
And the first big northern ice sheets formed when?
Around 3.6 million years ago, based on dating volcanic rocks mixed with glacial deposits. And this timing is fascinating because it coincides with major events in our own ancestry.
How so? Our ancestors were in Africa then, right?
It's exactly in East Africa. And it turns out that ice ages in the north correlate strongly with periods of drying, increased aridity in East Africa.
Why is that?
Changes in atmospheric circulation, less evaporation globally when it's colder. The net effect was that the tropical forests our early ape-like ancestors lived in started to shrink and fragment during these glacial pulses.
And this links to human evolution.
There's an amazing correlation. Independent evidence from molecular biology comparing DNA clocks of humans and apes suggests the big split, the divergence of the lineages leading to humans, chimps, and gorillas, happened somewhere between 3.5 and 4 million years ago.
Right around the time the Northern Hemisphere glaciation really kicked in and East Africa started drying out.
Precisely. It's hard to see that as mere coincidence. The environmental pressure cooker created by the onset of the ice epoch seems implicated in our origins.
What kind of pressure?
Think about it. Forests shrink. Competition for resources increases. Less successful groups get pushed to the edges into more open, mixed environments, woodlands, savanna.
Forcing adaptation.
Forcing versatility. You have to cope with different foods, different predators, different challenges. It would have been a strong selective pressure. Many lineages probably died out.
But the survivors
Would have been the ones who were more adaptable, more flexible, maybe starting to walk upright more, maybe using simple tools. Then, when the rains returned during the warmer interglacials,
forests expand again.
these newly versatile proto-humans could thrive and spread. Then the cycle repeats with the next glacial period, more pressure, more selection for adaptability, maybe for intelligence as a way to cope with that changing world.
So the Milankovitch rhythms, driving these climate pulses, acted as an engine for human evolution.
That's a compelling hypothesis. Repeated cycles of environmental stress and opportunity, gradually shaping bipedalism, tool use, bigger brains, leading eventually to us.
Quite a thought. Without the ice ages.
We might very well still be apes swinging in trees. Modern Homo sapiens emerged during the previous interglacial, around 100,000 years ago. We are fundamentally creatures of this latest ice epoch. Understanding that is really the triumph of the whole theory of ice ages.
So looking back over this whole story, it's been quite a journey of discovery, hasn't it?
A really long and winding road. From people puzzling over giant boulders to Swiss hunters and engineers noticing glacier marks, through Agassiz's grand vision, the astronomical detective work of Croll and Milankovitch, and finally the confirmation locked away in deep-sea mud.
And the realization that these immense climate shifts didn't just shape the planet's surface, but profoundly shaped us, our own evolution.
Absolutely. It connects geology, astronomy, climate science, and human origins in a really fundamental way.
Which leaves us with a final thought, perhaps. We know the natural astronomical cycles are still operating, slowly pushing us towards the next glacial period, eventually.
Over thousands of years.
But we also have the much faster human-induced climate change happening right now. So what's the long-term future for our current interglacial, caught between these natural cycles and our own impact? What challenges might that complex interaction bring down the road?
That's the multi-trillion-dollar question, isn't it? The interplay of those natural and anthropogenic forces is something humanity will be grappling with for a long time to come. Definitely something to ponder.